Hello, am I audible? Hello.
Yes, Himanshu.
Yes, yes, Himanshu.
Yeah, sure. So, hello everyone. In this class, we will going to start with the trusses problem. So, last class we actually looked some problem based on method of joints. So basically, that method is applicable when we have given the concurrent forces which are acting on the joint, and there we have used the force equilibrium equations to calculate the unknown forces. In this lecture, in this tutorial, I will try to solve question from method of sections. So we will solve the plenty of problems from the method of section, and also we will mix the methods. Like if you are using the method of section, there is no restriction that you can use only that method. You can use method of joint along with it. So based on this combination of method, one can solve the problem, and then we will actually move to the distributed forces. So basically, if we want to try solving problems on beams or even some problems in dynamics, we- it is actually important to know about some concepts like center of gravity, center of mass, centroid, and so on. Because as we study about the distributed forces, we want to model these forces mathematically. And to model these forces, we require to know about the centroid and centroid of mass. Even in the dynamics problems, we actually try to calculate the force or the kinematics quantities like velocity, acceleration of a particle. So whenever we say that we are going to calculate the velocity of a particle, let's say this is my particle, and we want to calculate the velocity of a particle given we have already given the force, we are actually referring to the velocity of this point. So this point is actually the center of mass or the centroid, or can be a center of gravity as well. So before moving to dynamics and the problems for beams, we will actually revise a few of some of these concepts. So this we will talk about after we solve few problems on truss from the method of section. So let's begin today class from the next question that we have left earlier. So here we have given the truss, and we need to find the zero force members. So in the last class, there was a question that how to visibly describe the force in the member of trusses. So basically, it is not possible to describe the force, or guess the force, but it's certainly possible to know that which are the zero force members. So in the last class, we have discussed that if you have given the member uh, follows this configuration, if you have three members here, so this is say A, B, C, and D. So when you use the equilibrium equation using the method of joint, you can actually see that the force in this member will be zero force member. So it will not participate in distributing the force, but this zero force member is very important to avoid the deformation of the trusses which are going to occur here in this trusses. So anyway, these kinds of deformation we are already ignoring for this course. Maybe in the higher level course you will learn about that. But in order to restrict the deformation, the zero force member is added, even though it doesn't have any contribution of carrying the forces. So in this problem, we need to determine the number of zero force members. And visibly, we can do that. For example, if we want to look such kind of an arrangement, so as we discussed, such kind of an arrangement will have zero force. So for example, here force in BD will be 0, and that we will look by using equilibrium equation, and it is not very hard to look. You can even guess from by writing the summation of force equation in the y direction and in the x direction. So you can actually guess from this truss. So here we can see that the member HG GF and CG have a similar configuration as I have shown in this figure, and we can predict that the force in this member CG is 0. So we consider joint G, and as we described earlier, when you consider any joint, first you need to define the Cartesian coordinate system or any coordinate system. Then you need to make a free body diagram. So this is my G. Let's say this is H, this is F, and this is C. And this is my coordinate system XY. Right, so if you do the summation of force in the y direction, you can see there is only one force you can consider here, and that is force in CG. That's all, and that should be equal to 0. There is no other force in the y direction, so you can straightforwardly say that the force in this beam CG will be 0. So this will be a zero force member. And for this reason, we actually described today or even in the earlier class that if you have such configuration or like this, the force in the member which is perpendicular to the HG and GF, or here it is AB and BC, will be 0. So we can actually conclude that this is our zero force member. Then from the figure we can actually guess that this system CD and DE and FD, again it has a similar configuration. You can see here CD and DE, and there is a normal member FD. So we can again predict the same thing, that the force in this FD should be 0. And again we can use equilibrium equation to find out the same thing. So we consider joint D. We make a free body diagram. Right, now we have to define the coordinate system. So in the previous class we actually defined the coordinate system in two ways. Like you can define in a regular manner, or it could be a tilted coordinate system along with the member, because we discussed that if we use this kind of a tilted coordinate system, that it become pretty much easy to do the calculations. So if I describe my coordinate system in a similar fashion such that my FD is along x-axis and DC is along y-axis. You can see now you don't need to consider angles or the component of the forces, because you made a coordinate system along FD and CD. So you don't need to find the component of FD and all. So again, if we write the equation or do the summation of force along x-axis, then you can see that force in FD will be 0, because there is no other component of force in the x-axis beside force in FD. So straightforwardly you can actually tell the force in the FD member FD will be the 0. So again this will be your 0 member force. Now from this figure there is another arrangement here: AB, BC and BH. It's the same arrangement. Now we can consider joint B and check that if the force is 0 here or not. Force in this member BH is 0 or not, because this is the same arrangement that we are talking about, like here and here. So now we consider joint B. So this is my joint B, and again we can use the tilted coordinate system. So this time again I can use this coordinate, which is, let's say, my minus x, and this is x, and this can be my y, or this could be minus y, because I don't want to deal with the components, or don't want to find out angle theta and describe the component of force. So I define this coordinate system. So if I do the summation of force in along the x-axis, you can see there is one force BH, which is minus, and there is another force 2 kilonewton here, minus 2 equals 0. So you can see that the force in this normal member is not 0 actually. It is equal to minus 2 kilonewton. Minus indicating that the sign we have considered in this member should be opposite. So it should be like this, going towards the joint, which make this force compressive. So you can see this has the same configuration, but still here in this member the force is not 0, and that is because of this external force. So if you remove this external force, which was the situation here at D and at G, the force in the member BH will be 0 if you remove the 2 kilonewton force. But if you don't remove, if you apply some external force like here, then force in the member BH will not be 0, even though it has the same configuration like this. Same configuration like this, the force in this member is not 0 because of the external force which is acting in the same direction. So now we can actually consider another system, another joint, because force here is 0, here is 0, and it is 0 here also. Let's consider joint F, because force in this member is 0. So we can ignore this member because we are only interested in calculating the force. So force in this member is 0. So basically we have again similar kind of a system here. So you can see this is not a normal, but it is actually have a similar kind of a system. So we can consider GF, FE and this member, and we can actually uh, predict, I mean we can actually calculate what is the force in CF, because here it is 0. The force in DF is 0. So we are actually ignoring FD in the member. Just forget about this FD if it is exist in this truss. And you will get another similar kind of a system here, like GF and FE, and there is a member of a member which is almost not perpendicular but almost perpendicular to GF and FE, almost similar. Here you cannot do this because here the force is not 0. So here we can predict that in this member also force will not be 0, because it is not a similar system that we are talking about, because in this member also the force is not 0, but here it is 0. So let's consider joint F and check if the force in member CF is 0 or not, because it is a similar system. So this is my joint F. So we have FG, FE and FC. And this is my coordinate system, the regular one, x, y, minus x, minus y. So let us define an angle, some angle here, theta, because here we need to calculate the component of the force. So if I write down the equation along y-axis, summation of force along y is 0, then I will have only force due to Fc. So it will be Fc cos theta equals 0. So you can again see that the force in Fc will be 0, because there is only one component of force which is actually acting in the y direction, and that is in this member Fc. No other force you can actually found in the along the y-axis. In the x-axis you can find the force Fg and Fe, but along the y-axis only force Fc is there, and that should be equal to 0 as per equilibrium conditions. So you can see this is the similar system, even though this Fc is not normal to Fg and Fe, but still if it is aligned with some angle theta, it's a similar system, and you can actually predict zero force in member Fc. Of course, if you now apply some external force here, let's say 5 kilonewton here, then the equilibrium equation will change. Now, then the equilibrium equation will become Fc cos theta minus 5 equals 0. So force in Fc will be 5 divided by cos theta. So it will not be a 0 because of this external forces. But if this external force is not there, then you will have a similar system that we are talking about since the beginning, and you can predict the zero force member, and your equation says the same thing. So if it is difficult for you, I mean, if it is still difficult for you to predict the zero force member, just use the equilibrium equation to confirm whether it is really a zero force member or not, because even if you use the equilibrium equation, you see that it is not a very big task. It is actually straightforward calculations. It's not like you will have to do a very complicated math. You just do the force balance along the normal member, or even if it is slightly inclined, do the force balance along that, and you can see that if it is the zero force member or not. The trick to remember, you should have this kind of a configuration, and force in this member will be 0. It should be like this, or it could be also like this, but this should be a in such configuration, force usually in this members should be 0 only when there is no external force acting here, because we saw that if external force is acting here, then it is not a zero force member. It will have some force. The force will be distributed in this member. But if there is no external force, then this should be a zero force member. And that you can check also using by equilibrium equation very easily. So, any doubt in this question? If not, then we can move to the next question. So in this question, we actually need to find the force in the member HD, CD, and GD. So we need to find the forces in this member, and we will actually find the force by using method of section. So method of section is usually used to find the force in a particular section or in a particular member, because you can see sometimes the truss are very complicated. For example, in this question, you can see it's a very complicated truss. So there are a lot of members in this truss, and if you use the method of joint, you need to consider each joint here to calculate the force in each of this member. And the method of joint will take a lot of time. It will become a lot, complicated a bit, and it will take a lot of time to calculate the force in each member, even though it uses the same method that we have doing since last 2 or 3 classes. It uses the equilibrium equations, but you can see it is very a cumbersome method, because for such complicated truss you have to consider many number of joints and calculate the forces in many members, and it will be a very time consuming method. So instead of it, we can use the method of section, where we cut the section into a half. So let's say, so here we need to describe the force in this member HD, CD, or this GH. No, it's a GD actually. Let's say it's a GD here. So we can actually cut the truss into a half like this, such that this line actually passes through at most 3 members. So this is the way you cut the truss. You can actually make a cut in anywhere. You can actually make a cut here or here or here also. But usually it is preferred to make a cut where you have these unknowns, most of the unknowns. You can also make cut like this or like this. So there is no restriction how to make a cut. The only thing that you have to make a cut and divide the system into a 2 parts. So here we make a cut, because you can see while making the cut, you can actually making a cut along this HD, along HD and CD. So always prefer to make a cut along those members which you have to find, the forces which you have to find. So we have to find the force in HD, CD and GD. So we make a cut which goes through HD, CD. So that's why I choose a cut like this. Now once you cut the truss into 2 sections, you actually divide the truss into 2 sections, this left section and this right section. You can actually assign the forces from those members in which you have cut. So I have make a cut from GH, this HD and CD. Then we can assign the forces here. Let's say I assign the force like this. So it could be this. So once you assign the force, now you can use the equilibrium equations here. So now you can also use the moment equation. So in the method of joint, we mostly use summation of force equation. But now you can also use the moment equation about any point. So you can take any moment at any point. It can be A, it can be E. It actually define the what force. I mean, it defined the forces or the members. It defined on the member you want to calculate the force. So for example, let's say uh, let us actually first calculate the reaction forces. Now, since you have cut the force into two sections, what you can do, you can actually calculate the reaction at E and A. Because when you consider the movement at about any point, let's say G or D, the reaction force at E or A will also create a movement along it, and it will influence these forces also, because the moment equation you are using, it should contain the moment due to reaction forces as well as the known forces that you have in this truss. By known forces, I mean these external forces. So when you use the method of section, it is always preferable to first calculate the reaction forces. So you can see that this is my AY and this is my EY. So if I take a movement along A, I can actually calculate EY. Right? And the forces which cause the movement along A, so this force will not cause any movement along A because the perpendicular distance from 30 kilonewton to A is 0. But this and EY will cause a movement. So you can see that 20 kilonewton force has a perpendicular distance of this, which is 4 meter, and it will rotate in a clockwise direction along point A. So if I consider clockwise movement, clockwise rotation as positive and anti-clockwise as negative, so I will have 20 multiply 4, and this force also have a clockwise rotation along point A, so it's plus, sorry, 20 multiplied by the perpendicular distance is 8 meter, and the same can be concluded with this force. It has a clockwise rotation, so it's plus 40 multiplied by perpendicular distance, which is this, and it is actually 12 meters. But with EY, you can see the direction of EY is towards up, it's in the upward direction, and this will rotate along point A like this in the counterclockwise direction. So it will be EY minus EY multiplied by 16 equals 0. So this will be 16 EY equals, and we need to solve this equation to get EY. So when you solve, you will get EY as 45 kilonewton. So now you can find out the EY, which is 45 kilonewton. Now we can actually find these unknown forces in GH, HD, CD, and then in GD, because you have make the cut along these three members, and you assume that in this three member you don't know the force, so you we can actually find. So here in this method again we have to use the force balance and the moment equation, and the use of the moment equation will simplify the calculation because we already made a cut, and now we can use the moment equation about any point to calculate the force. So for example, let's say if I use the movement along point H, then the force in there is no contribution of force GH into the movement, because the perpendicular force from force GH to point H is zero, right? So the only force which create a movement along point H is EY and 40 kilonewton force. So here I'm only interested in right side of the truss because I made a cut. Now you have to choose which section you are interested in. You can take movement along any point. You can take a movement along point A, J, I, H, C, B, G, F, D. But you have to choose the section. So I choose right section because in right section I have to deal with only 40 kilonewton external force. That's all. If I choose the left section, you can choose that. It's on your choice. But I have to deal with 30 kilonewton, 20 kilonewton. This again 20 kilonewton, and then I have to find AY because I already find EY, so I have to worry about EY and 40 kilonewton force only. So if I choose point H, then the force HG will not create any movement along point H because it does not have perpendicular distance. And I can say the same thing about force HD. It has zero perpendicular distance, so it will not create any movement along point H. But EY, force EY will create a movement along point H. You can see it has a perpendicular distance. Let me just erase a lot of things here. So you can see that. So this is my cut numbers. So EY has a perpendicular distance from H to EY, which is this, which is 8 meters. So EY will have a movement along point H. Then 40 kilo Newton force will have a movement because it has a perpendicular distance of 4 meter. So we have a 40 kilonewton force which is creating a movement along point H. Then there is a force CD, and this is the perpendicular distance for CD because the force is in the x direction or in the horizontal direction. So this will be my perpendicular distance, which is again 4 meter. So these three force will actually have a non-zero movement along point H. So the movement at H will be given as, and assuming the same sign convention where the clockwise is positive and anti-clockwise is negative. So when we do that, you can see that. So I'm interested only the right section. So in this section I'm interested. So you can see CD will rotate in a counterclockwise direction about point H. So it will have a negative movement. This is having a negative movement. EY also rotating in a counterclockwise sense around H. So EY will also have a negative movement. And we have 40 kilonewton, and 40 kilonewton will rotate like this around point H in a clockwise sense. So I will have 40, its perpendicular distance is 4, minus EY multiplied by 8. Sorry, EY we already found, which is 45. And then CD, So you will get CD as minus 50 kilonewton. So the CD is minus 50 kilonewton, which means the direction should be reversed. So it should be in this direction, which means it is away from joint D, which is tension. So this is tensile force. So we found the force in CD. Then we can think, now we have to find the force in HD. We already found force in CD. Now only HD and GD remains. And then you can think how to calculate the force in GD and HD. So you can see it's nothing fixed here. Like what point you have to take movement, where which joint you have to consider to do force balance. Nothing is actually fixed. You have to decide yourself to analyze how should I find. For example, let's say if I uh, do the force balance analysis in the y direction. So I consider the right section of the truss, and if I do the force balancing along the y axis, then I don't need to consider force along. Let me just clear. So if I do the force balance in the y axis, I don't need to consider hg force because it's not in the y direction, the force hg in the x direction. And I don't need to consider force in CD as well. We already found the force in CD, but we don't need to consider CD. We only need to consider force 40 kilonewton, the component of this force HD, the y component of force HD, and the reaction force EY, right? And we are only concerned about the right side of the truss because we made a joint and we differentiate the truss into two sides, and we are only concerned about the right side. So right side of we have only 40 kilonewton, reaction force EY, and the component of HD force, y component of HD force, which is in the y direction. So when I write down the equation, which is summation of force in the y direction equals to 0, I have to consider only three forces. So if the summation of force in the y direction should be equates to 0, then I have minus 40 plus EY, which is 45, then this force, which is, let's say this is my theta, and this should be 45, right? So if you have this angle as theta, because you want to find the component of force HD, this and this, and this side is 4 meter and this side is 4 meter, then you will find theta will be 45. So this will become sine 45, and it's in the upper direction. So HD sine 45 minus 40 plus 45, which is my EY, equals to 0. We are just doing the force balance in the vertical direction. So it is HD sine 45 plus 5 equals 0. So HD sine 45 minus 5. So when you solve this, you will get minus 707.07 kilonewton. Again, it's a minus sign, which means we assume the wrong direction. It should be like this, towards joint D, which is compressive force. right? So you already found the force in HD and CD. Now only force in GD remains, right? So you can now think, now what approach should I use? Should I take a movement along any point, or if I use the force balance like we did now? If I use the force balance in the x direction, I can't find the force in GD because the force GD it's completely in the y direction. If I do the force balance in the y direction again, we actually cannot find the force because we made a cut. So the unknown force we described is along HG, HD and CD. If I use the moment equation, let's say, then again there is no use because we have not described unknown forces here. But I can choose joint D and then use the method of joint, right? Because I already know the force here in joint HD. Here I already know the force. I already know this force also. I have to find the force in GD here. I don't know the force here because if I use the method of joint, I in the equilibrium equation I have to consider this force also, right? D and E. But since I need to find the force GD, which is completely in the y direction, so if I do the summation Fy equals 0 by using the method of joint in joint D, I don't need to consider these forces because these are not in the y direction. So if I use the method of joint along point D, first I have to make the equilibrium diagram along D. So let's say this is D. We already found CD, which is the tension force. Then let's say this is my DE, this is my GD, and this is my HD, right? So you can see from this free body diagram that even though we don't know force in DE, and our objective is to find the force in GD, this is our objective, but we can still use the method of joint even though we don't know this, because if I do the summation along y-axis, I don't need to consider these two forces because it's completely in the x direction. And this I know, theta, which is 45, and this should be also 45. And I already know HD. I already know HD, which is 7.07 kilonewton compressive force, right? So it will come out minus HD cos 45 plus GD equals 0. So GD will be HD cos 45, HD is 7.07 cos 45. So when you find, you will get GD as 5 kilonewton. It's a positive 5 kilonewton, which means the assumed direction is correct, and it is, you can see it is moving away from joint D, which means it's a tensile, right? So here we actually find the force in three members, which is GD, CD and HD, by using method of section. At last we also use method of joint. So you can see that, so just to revise here, uh, when we use the method of section, first we cut the truss into two parts, and we cut in such a way that we can actually find more number of unknowns. saw that it cut through HD and CD, which are the unknown of interest for us, and then the another unknown was GD. So then we divided left truss into two parts, which is left side and right side. So in order to use the moment equation freely, it is convenient to find the reaction force. So I consider right analyzing the truss in the right side part. So I actually find the reaction force EY from the moment equation. So I take the moment along point A and calculate the force EY. Once I got EY, then it's up to us how we should calculate the force. So we can see that force in this member is unknown, force in this member was unknown, and here also it was unknown. And we also need to find the force here. So the line where you make a cut, the members it passes through, those members have unknown forces, and we need to calculate those unknown forces. So first we take a moment along point H and we actually calculate force in the member CD. Then we see the diagram and we found that if I use the summation of force in the y direction and equate it to 0, then I can actually find another force, and we found the force HD in the member HD. Just to be noted that you have to use either side of the truss. So we are using here right side. You can do the same similar analysis in the left side also, but you can see in the left side there are too many external forces are there. So they, here the mathematics will become even more, I mean not much but little more difficult, because you have to deal with a lot number of forces. And at last we actually use the method of joint. So we actually select point D and then we do the usual procedure where we make a free body diagram and we use equilibrium equation to calculate the force in GD. So this you have to actually think, because once you cut the force, there are number of ways you can actually find the force in the unknown numbers, and that you have to decide how to do that. You can use the moment equation. You can check if you can do the force balance analysis in the y direction or in the x direction in one specific part of the member or in specific part of the truss. Then you can check if I choose any joint, can I use the method of section and calculate the unknown force? Is it convenient to do that? So there are multiple ways you can do that. And to find the force in these three members, HD, CD, GD, we use three different approach. First, we use the moment equation about one point to calculate the force. Then we use the force balance equation in the right side of the truss to calculate the unknown. So when you use the force balance equation and you are not using here method of joint, just you are doing the summation of force, you have to select the which side of the truss you should consider. So here we consider right side. So first we did moment balance, we found force in CD. When we do the force balance in the y direction, in the right side part, we calculate the force HD. Then we use the method of joint where we choose joint D, and then we use the method of joint at joint D to calculate the force in GD. So you can see in all of these three members we use three different technique, and those three different technique you have to decide. So any doubt in this question?
Hello, Himansu.
Yeah, yeah.
Can you hear me? My Sumaran.
Yes, 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 yes.
Uh, so the question is what the trusses they have to find HD, CD, and GD forces only. That is the question. All right.
Yeah, yeah, yeah.
If I want to find BI or BH, can I found it the same method?
Yeah, yeah, you can use this method to calculate the force in any members. For example, let's say you want to let's say you want to find the force in, let's say, BI. you want to find the force in BI,
Yeah,
BH, and let's
yeah,
say BC. Then you cut the
yeah.
truss like this. You cut here, and then you
Okay,
define the unknown forces along those members which you make the cut. So these are the unknown forces, and then you can uh, use the similar method. So you just calculate the reaction force. So let's say if I use the left section now, I can calculate the reaction force AY here. Then you have to use the inspection how to calculate now. So for example, let's say if I want to calculate the force in BI, so I
yeah.
can use the summation of force in the y direction in the left side of the truss. When I do that,
Oh,
I have to consider AY. I have to consider this 30 kilonewton, 20 kilonewton, and then I have to
mm.
consider this force, which is BI. Then
So
this, yeah,
we have to consider left or right with respect to the construction. If we cut that part, then we have to take the left part as a left and right part as a right.
yeah, you
So
can,
if you cut in between that BC HI means we have to take 30 kilometer and 20 kilometer as our salvation. Am I right?
yeah, yeah. I mean, it depends what members you are looking. So you are looking
Okay,
BI, so you can consider left section.
okay,
If you are
okay.
looking CH, then you can consider the right section only.
Okay, okay. Next question is how we initially decide the direction and how it come to it is compressive or tension. How we you
So,
just put initially some direction, but then you calculate. No, it's become compression. It becomes tension. So how you decide? That is my
so this I explained in my last class because so in the last class I explained that let's say this is your joint,
okay,
and if the force is in the direction it's toward this joint, so you this is your member, let's say this is your truss, and you are doing the analysis at this joint, and you can see if the force is towards the joint, then it will be a compression, and if force is away from the joint, then it will be a tensile. So for example here, so it is
no,
going towards, huh?
Himanshu. I just understand that the force is towards this joint is compressive and away from its tension. But initially, how we decide? That is
Oh,
only
initially I have
how.
just guessed the direction.
Uh, first we have to guess the direction. After we come to the solution, then only with respect to the signature sign convention only we have decided. Though no, we are deciding our guessing direction is wrong, so we have to change to tension or compression. Am I
Yeah,
right?
yeah.
Okay, okay, okay. Uh, yeah. Today's section we have discussed only this type of question only, not that related to the
I don't know
assignment
about the
question.
assignment. I mean,
Oh.
I don't have any idea about the assignment questions.
Okay, okay, okay. Because we need some clarification regarding assignment questions. We posted in the question answer page, but there is no reply. That's only I'm asking.
Okay, okay, okay. I will see. I mean, I'm not handling the assignment part, but I can
Okay,
check when they should
okay,
put the solution of assignment.
okay, Mans. Thank you.
Yeah. So let's move to the next question. So here, let's say we need to find the force in the member BCCG and GF. Then so this is the members BC, CG and GF. So we can make a cut like this, and we can assign some directions here. So these are the forces we need to find in the respective members. So we can use the same trick. So first we can actually find the reaction forces AY. and EY, and then we can consider only the,
Hello, Imans.
yeah,
Imansu?
hmm, yeah.
That in A that is fixed frame of reference. That in E that is conical section. Which means we have to put reaction EY and EX or only EY.
So EY, here we need to put only EY. It's a roller
EY
joint,
only.
so
It's a
EY
roller
only.
joint. Roller joint.
Yeah.
Okay, okay.
Here
It's
you
one
need to
type of
consider AX. So
egg.
in pin joint you have a two component AX and AY, but
Okay.
for EY you
Okay.
have only one.
Because of rolling joint.
Yeah, yeah.
Oh, thank you.
Yeah, so let's find the reaction AY. So I can take the movement along point E. So the force which will contribute to the movement along point E will be 6 kilonewton force because it has a perpendicular distance this, which is 6 meter, then 8 kilonewton because it has a perpendicular distance of this. AY will have, AX don't contribute to the movement because it doesn't have a perpendicular distance to point E. So again I will use clockwise as positive and anti-clockwise as negative. So if I sum the moment along point E, equilibrium states it should be equal to 0, and we can see the direction of force 6 kilonewton is in the downward direction, and it will rotate around point A in a anti-clockwise manner, and same with 8 kilonewton force. It will rotate around point E in the anti-clockwise manner, but AY rotates along point E in a clockwise manner. So it is AY multiply 9 minus 6 multiply 6 minus 8 multiply 3 equals 0. So it will be AY 60 by 9 will be 6.66 kilonewton. And AX will be 0 because you can see there is no force in the horizontal direction. So the only force in the horizontal direction here is, for now, is AY. So after that I make a cut, I define the force here, which are the unknown force here. And now our objective is to define the force in BC, GC and GF. And I will choose the left side of this truss, right? So if I again, then we have to check how should we went, or how should we start calculating the force. So I can calculate the force in GF if I considered the movement along point C, because then the movement of force B, I mean, if we consider force along BC, the movement due to this force will be 0 about point C because it doesn't have perpendicular distance, and the movement from force GC about point C, again it will be 0 because it doesn't have any perpendicular distance. But we have to consider the movement from force GF because it has this perpendicular distance, which is 3 meter. So force GF will have a movement along point C, then AY will have a movement, it has a perpendicular distance of this, which is 3 plus 1.5 meter, and this 6 kilonewton will have a movement because it has a perpendicular distance of 1.5 meter this. So if I take the summation of movement along point C, which is equates to 0, then let me clear the diagram. Then AY rotate in a clockwise manner about point C. It's rotating like this. And 6 kilonewton rotate in an anti-clockwise manner about point C like this. And we have assumed the direction of GF such that it will rotate in a clockwise manner about point C. So AY multiplied by 3 plus 1.5, 4.5 plus AY we already know it's 6.66. Then GF is again the clockwise, so it is positive, so it will be GF multiplied by 3. And 6 kilonewton, so this is rotating in the anti-clockwise manner about point C, and it has a perpendicular distance of 1.5 meter. So it is minus 6 multiplied by 1.5. It is approx 30 minus 9. So force in GF will be around 7 kilonewton. And this is negative, which means the assumed direction should be different. It should be like this. That is, it is actually going away from point joint G. So it's a tensile. So we calculated the force in GF, member GF. Now we still left with force in member CB and CG. So if I use the summation of force in the y direction and consider left side, I don't have to consider again the force in BC. I can consider the component of this force in CG, and I have to consider force AY and 6 kilonewton. Then I can easily form, because the only unknown is force GC. So if I do the summation of force in y direction and I consider left part of the truss, then I have AY 6 kilonewton force and this component of force GC. So you can see the sides of the triangle are 3 meters. So each of these angle should be equals to 60. So this component of y component of GC, it should be GC sine 60. That's my y component of GC, and my assumed direction is upward. So it is AY plus GC sine 60 minus 6 kilonewton. So if I bring it to right hand side, it will be equal 6. So GC sine 60 equals 6 minus 6.66. So it will be equals to 0.66 minus. So it will be GC equals minus 0.762 kilonewton. Again, we can change the direction here. So it will be this towards the joint G. So it will be compressive. So now only member left is BC, and here we need to think how to calculate the force in BC. So if I consider x direction, for summation of force in x direction, then I have to consider force in BC. I have to consider the component of force in GC, and that's it. So this will give me, so I already know the force in GC, so I can calculate the component of x component of GC, and that will be equals with the force in CB if I do the summation of force in the x direction. So if I do the summation of force in x direction and equates to 0, considering the left side of the truss, this is my assumed direction. So it is FBC positive and negative x component of GC. GC cos 60 equals 0. GC is 0.762 cos 60. So it will give me 0.381 kilonewton. It's a positive, so we don't need to change the sign, and it is going away from joint B. So it is a tensile force. So just to recap here we need to find the force in BC, CG and GF. So we make a cut along those member only. And then as usual, we actually find the reaction force AY and EY, AX. So you have to find the reaction force before even making the cut. So first you have to find the reaction force from the pin joints or the roller joint. Then once you find the reaction force, then you cut the truss and differentiate into left side and right side. And the members in through which the cut occurs, you have to define those members as a undefined or unknown force members, and then calculate the force in those members. So first we choose point C, we take a movement along point C, and we can able to calculate the force in member GF. Then for the remaining unknown, we actually do the force balance in the y-axis and force balance in the x-axis and equate it to 0, and we can able to get the force in other members also. So again, you can see that it's all based on the inception, that what method you have to use to calculate the force in the unknown members. So any doubt in this one? If not, then we can move to the next question. So here we have given the walkway exerts vertical 50 kilonewton load on the variant truss at B, D, F and H. Use the method of section to determine the axial force in member CE. And we can also find the force in member BD as well. And it has been given in the question that at point B, D, F, and H, there are external forces of 50 kilonewton, and we need to find the force in CE, and let's say we can also find the force in BD. So we can cut like this. We can make a cut like this. But before we made a cut, let's find the reaction forces here. So it will be AY and IY. So let's find AY here. So we have to take the moment along point I. Again, the clockwise movement will be positive and anti-clockwise will be negative. And you can see all this force will rotate in anti-clockwise manner along point I. So all the movement due to all this force will be negative and movement due to force AY will be positive. And AY has a perpendicular distance of 6 multiplied by 4, which is 24 meters. So the summation of movement at point I should be equals to 0. So we have 24 AY minus 50. So this should be 1821 meters. 15. This should be 9. So this is 3 meters. This 3, this 3. So it's 9 minus 50 multiplied by 3 equals to 0.
Hello,
Hello?
Himanshu.
Yes.
The video is, I think, video is stuck.
Oh, okay, okay. Mm, just a second.
Okay.
Yeah, is it fine now? Okay.
It is now visible.
Yeah. So I've been finding the reaction. So I fix point I and I'm taking the moment along point I, and I'm actually trying to find the reaction force AY. So this will come out to be 100.
Himanshu, I think you muted. Hello?
Sorry, yeah, yeah. So I've been trying to calculate the reaction force AY here. So I choose point I and for the moment. I took the moment along point I and I'm trying to calculate the reaction force. So from this we can able to calculate the reaction force AY as 100 kilonewton. So once we calculate the reaction force, let's say AY, we need to find the force in the member CE and BD. So we make a cut like this. Let's say these are my directions. So if I take the point D and take a moment along point D, I don't need to consider member BD. I don't need to consider member CD also. And I can, so there will be a force along CE which can create a moment along point D. So then there will be a reaction force AY, this 50 kilonewton force, and force in CE, which is creating a moment along point D. So this will be moment at D. The summation of moment at D should be equals to 0, and AY will rotate in a clockwise manner. CE will also rotate in a clockwise manner about point D, and 50 kilonewton force will rotate in the anti-clockwise manner. So this will be AY, but we need to find the angle also, right? Because we don't know these angles. But for this moment equation, we don't even require now. We will require it later maybe. So let's focus on that only. So we have AY multiplied by 6. So this is my perpendicular distance. So it's 6 plus 3. So it's 9. Then due to 50 kilonewton force, which was rotating in the anti-clockwise direction, we have the perpendicular distance of 6 meter. So this is 3 and this is 3. Is minus 56, and CE we assume the direction like this. So it was rotating in a clockwise sense around point D, and the perpendicular distance is this, which is 2 meter given here. Equals to 0. AY we know it's 100, so it is 900 minus 300 plus 2CE equals 0. So this 600 minus 2CE. So this will give CE as minus 300 kilonewton. So CE will be, so we have to change the direction. So we assume like this. So it should be away from the joint. Joint C. So it is a tensile. Then we need to find the force, let's say in BD as well. Here.
Hello, Himanzu.
Yes,
Uh, though we consider the left side of the construction, why we have to take the moment from D? Why not take the moment from D?
you
If you
can take.
take the moment from D only, we get CE. Am I right? Or we just calculate the CE from B moment also.
Yeah, you can do that. You can also take the moment. So as I said in the previous question that it is not a rule from where you are calculating movement. So nothing is
Because
predefined here. You have
because
to.
the confusion is We are considering the left side of the section. Why we are taking the moment from D? That's my question.
No, so you have to consider left side on of the section when you do the
Okay.
force balance analysis. Even if you
Okay.
take the movement here, you are taking only those forces which are in the left side direction. So even if I take the movement along point D, I am only
Hmm.
considering the forces which are in the left side, left hand side,
Okay.
which is AY 50 and this.
Okay.
But you can choose any point to take the movement. You can even choose point G, H, and F, but you have to consider only the forces which are at the left hand side. I am
Okay.
actually choosing point D so that I can ignore the force in BD and CD. So that only force I need to consider is CE, AY and 50 kilonewton.
So, which is preferable and which is taking more complicated? That is the option.
So
All
if
right.
yeah, this is just for the convenience of solving. If I take the
Okay.
moment along point P, then I can ignore this thing, force in this expression. I can also ignore force in this term, but I mean, yeah. So the thing is, if I take the moment along point B, so the unknown forces are in this members. I have to use the force, this force also, force in CD. So
Okay.
the force in CD is unknown and force in CE also unknown. So
Okay.
both are unknown forces. So that I cannot solve from one moment equation.
Okay.
So this,
Okay.
yeah,
Okay, Mans. I understand. I understand. So we get more unknown, then we can't solve. So we
yeah,
have to reduce the unknowns.
yeah, yeah,
So we have to choose the preferable one.
yeah, yeah.
Okay. Thank you.
So we already now know CE. Now we need to find BD. BD is in the X direction. So now what should we do here? Hmm, we cannot take summation of force in the X direction because then there will be a force CD which is unknown. We don't know anything about CD, so we will get the equation like CD. So let's say if this is my theta, so it will be like CD cos theta plus PD equals 0. You will get this kind of an equation if we do the summation of force in the X direction. And both CD and BD are unknown. So we cannot find BD from this expression. So if I take the moment along point C, then I don't need to consider the force in this member CD and also CE, because the moment due to force CE and CD along point C is 0. So then I have to consider force in BD because it has non-zero movement along point C. I can consider force, reaction force AY and 50 kilonewton force also. So again, if I choose to equate movement along point C and equate it to 0, then I have the contribution to the force BD. So BD will rotate like this along point C, like in the counterclockwise direction. So it is minus BD multiplied by 2. AY is rotating in the clockwise sense along point C. So it is AY multiplied by 6. AY is 100, so it's 600. And then it's a 50 kilonewton force rotating in the anti-clockwise manner about point C. And it has a perpendicular distance of 3 meter. So it's minus 50 multiplied 3 equals to 0. So it's 450 equals 0. So BD will be 450 by 2. It's 225. kilonewton, and we don't need to change the direction, so our assumed direction is correct, and our assumed direction is towards point B, which is compression. So that's it there. So here, just to recap, here we have to find the forces in member BD and CE. So we make a cut along BD, CD and CE. So before making the cut, we found the reaction force AY, then we make a cut, and we first take a point along D, so we can uh, remove the contribution of force BD and CD in the movement, and we have only uh, contribution from the force from CE, and other forces we already know, like AY 5 or 50 kilonewton. So we actually knows that moment, so we can find CE from the moment equation if we take the moment along point D. And then we saw that if I do the summation of force in the x direction, we cannot find the force in BD, because even though the force in BD is completely in the x direction, there will be a contribution from the x component of CD, and we don't know CD also. So this force BD actually balanced by the x component of CD. So if you do the force balance in the x direction, it will be like this, and we don't know CD, so and we already don't know BD, so we cannot solve this equation. So we choose point C and take the moment, so we can remove the contribution of the force from CE and CD in the moment, and but we will have the contribution from the force BD into the moment along CE. So we did that, and we can able to find BD as 225 kilonewton. So any doubt in this question?
Hello, Imansu.
Yeah,
The question is in B, D, F, H, they are each carrying 50 kilonewton.
yeah,
Uh, there's an alternative. If you consider that UDL load means how to convert.
yeah. That we will see in the next tutorial when I will solve problems of beam. But as of now, it's not a UDL. You can see it's a 50 kilonewton force. If it has been a UDL, then the intensity can be given in terms of 50 kilonewton per meter or per meter square, like
Uh,
that.
yeah. That's my question. That's my question. So we have to consider also UDL. If UDL comes, we have to consider that, and we have to convert to point load, and
Yeah,
then convert to the construction,
yeah,
and
yeah.
find the actual member
Yes, yes.
force.
Yeah,
Yes. Okay. Thank you.
yeah. So now that we can discuss about it, so there is another question from the trust. So you can use this question for practice. So here you need to calculate the force in member AB, BC, and CE. So you can actually make a cut like this, and you just define the arbitrary direction of forces, and you can use the method of section to uh, calculate the unknown forces in this member. So just before make the cut, just first calculate the reaction forces here. Once you calculate the reaction force, then make a cut like this, because these are the unknown forces that you need to find out, and then use the above approach that we have been using since 3 or 4 questions here to calculate the unknown. So once you make a cut, then it's up to you how you are going to approach to calculate the forces. You can choose one point and use the moment equation to calculate, or you can directly do the summation of force either in the x direction or y direction and see whether you can calculate force or not, because sometimes what happens when you write down any of this equation, you will get two unknowns. Let's say here you know z, but you don't know x and y, so you cannot use this equation because you have only one equation and two unknown. So in that case, it is suitable to choose another point somewhere in the truss, and then maybe use the moment equation around that point, and then you can find the unknown. So this question you can use for the practice. So I will upload this PDF, and you can use you can practice this question using the method of section. So after that, we can actually move to the distributed forces, because this can be used to calculate the forces which exerted on the beam, and also some of the concept in the dynamics, because usually we calculate velocity, acceleration, and various kinematics quantities along some specific position of the body. We don't need to consider the entire body and calculate the velocity and acceleration. So whenever we say that the velocity of the particle is this, or the acceleration of the particle is this, we actually refer to the velocity of this point, center of mass. So we actually track the center of mass instead of the entire body. So this is actually the one kind of an approximation we use to model the problem. Similarly, let's say you have a tire here. This is some wheel or some tire, let's say. We assume that there is a point reaction force between the tire and the land, but actually, if let's say the tire is soft, there is a distribution of force which is acting. Here the distribution of the force which is acting, and that can also be true for this kind of a pin joint, because if you zoom out this pin joint, so let's say this is a pin joint, and here also there is a distribution of forces which is acting. So this kind of distribution of force in various systems, like here in pin joint, or in this example, or in the example that we will look in the beam where we have a UDL, distribution of forces which are acting. So this kind of distribution is our objective is to model this kind of forces. So the one common objective is, I mean, one common method is use this distribution of forces. This distribution of force can be indicated by the intensity of force, which is, let's say, W here. So we can actually convert this intensity of force into a point load, which is the resultant force. Let's say this is R, this can be R as well, and this can be R as well. So for that we need to use the concept like center of mass or the centroid to do this. So we can go through this concept first. So the center of gravity is basically the location of weight which is concentrated on the body. So the position of that concentrated weight will give you the position of center of gravity. Let's say you have an arbitrary body. So let's say this is z axis, this is y, this is x. We have a body here. Say this is G, which is the center of gravity in which the weight is acting. And if you consider a very small element from this body, then it will experience small force. I mean, this is a small element, so you will experience the force on this small element as dw. And w is the weight, which is basically the mg. So the location of this weight can be traced out in this curve. So this is y bar, and this is x bar. This is y, and this is x. And here our objective is to determine x bar and y bar, basically the location of center of gravity or center of mass. So For that we will be using the moment equation. So we says that the moment of resultant gravitational force, which is W, about any axis, it could be x, y or z, equals to sum of moment about same axis of gravitational force acting on all particles. So basically we are saying that the movement due to force W about some axis, let's say y axis, is equal to sum of all the movement due to the force carrying by each of this particle, due to the gravitational force carrying out by each of this particle. So when you calculate the sum of all the movement due to this gravitational force of all the particle about the y-axis, it should be the equal of a movement due to force W about the y-axis. So mathematically one can write this as Wy bar equals to sum of all movement, which is y dw. Or if you want to do the movement along the x-axis, then it could be Wx bar equals to x dw. So this summation will contain all the gravitational force of this particle, and x multiplied dw basically is the movement due to all the forces of this particle, small particle that we are referring in this body. So this is the equation that we need to find, from which we can actually find x bar and y bar. So from this equation we can write x bar as x dw multiplied by, sorry, divided by w. Y bar equals y dw divided by w, and z bar equals z dw divided by w. So this is the location of center of gravity. Now let's say if you substitute dw as gdm, because you know the weight can be given by mg, so dw is g dm. So if you put in the above equation, you will get x bar equals x gdm divided by mg. So g, so here we approximate that g is uniform, there is no variation of g. G is same everywhere, so we can keep g out of the integral, so it will be g x dm mg. So this g and g will cancel out, so it will become x dm divided by m. And similar operation can be performed with y expression. So this y bar will be y dm divided by m. Z bar equals to z dm divided by m. And these are the location of center of mass. So you can see that if g is uniform, you neglect the variation of g, then center of mass and center of gravity both are the same thing. But if g is not uniform, g is varying in spatial direction, then you cannot put this g out of the integral. You have to consider this g inside the integral. So this will be your expression. So here you will have g inside the integral. And in that case, your center of gravity and center of mass will be different. So in our problem, whatever the problem that we are going to consider, we will assume that g is uniform. So we will be only using the term center of mass instead of center of gravity to avoid the confusion. So because in that case both will be the same. Again, we can use this expression. So let me use this expression here. So if I write dm as rho dv, so mass can be given as density multiplied by volume. So dm will be rho, and small volume I'm writing as dv. So if I use this equation, these two equation here in this one, then I can write the expression of alternative expression of the center of mass. So it will be x bar x rho dv here, or it could be just rho multiplied by v because this is the mass. Y bar equals y rho dv rho v. Z bar equals to z rho dv, and this is rho v. Again, these are the same expression. Now I'm assuming that the variation in the density is also constant. It's a uniform variation. Let's say if I consider this beam, then I assume that the density of this beam is same at every point. There is no change in the density as I move in the x direction or in the y direction. So when I assume like that, I can put this density outside this integral. And when I do that, then this expression will become x dv divided by v. Similarly, this will become y dv divided by v, and this will be z dv divided by v. So you can see now this expression is function of geometry only. It is not a function of density, mass, gravity. It is only a function of geometry. And this is called centroid, location of centroid, which is the geometric property, not the property of the body like mass, density. It's a only geometric property which is called as centroid. So now our objective is to calculate x bar, y bar and z bar. So we can start with very simple example. Then in the next class we will proceed with little more complicated examples. So we can start with very standard example that you can find in any book. So we can have, this is my x, this is my y axis, and I can have a triangle here. Let me define very small element. So usually in this problem, I define the small element as a line. I can also define the small element like a shape of square or shape of triangle. But the problem is in order to evaluate this small patch, you need small area element. So you need an integral like dx dy. It's like a double integral you have to do, dx to dy. But if you define the small line element, you have only small quantity which is dy, and to evaluate this line element you have to do only single integral which is dy. You don't need to consider this area because you assume that this is very thin line element. This is y, this is b, and the total height is h, and this is our x. So here, since it's a line element, you have only single small element here which is dy. So your area, the small area, can be written in terms of x dy. If you have considered this patch, small patch, then this dA will contain dx and dy. So you have to do the double integral to solve the problem. But since this is a line element, not an area element, so you have only dy. So area can be, So this small area can be written in terms of small line element, which is dy. Then you can use this relation ax bar equals x dA. So ax bar is x, sorry, this is dy, should be x dy. So now you can actually use the property of triangle. It says that x divided by h minus y equals to b divided by h. So you can write x as b by h minus y. So this integral will become, let me write here. So area of triangle can be written as bh by 2 multiplied by x bar integral h to 0 and x dy. So I can write x from this expression. So it will be b by h minus y dy. And this is actually y bar. I am actually looking y bar, so there will be y here. It will be y here actually. And this will be dA. And dA is x dy. So this will be y x dy. So now you have to integrate this. So it will be h by 2 y bar equals h0. So I can remove this h outside. So it is yb h minus y dy. So it is 1 by h 0 to h. It will be bhy minus by square dy. And when you do this integral, you will get bh square by 6. So this is bh by 2 y bar equals bh square by 6. So from here you will get y bar as h by 3. So this you can remember that for triangle the centroid of y is h by 3. So for triangle it's h by 3. For rectangle it's h by 2. And for circle it's h by 2, given that h is the diameter. So it's h by 2. So these are the standard results that you can actually remember, because when we are converting the distributing load to the point load, we actually require this location of centroid. So the location of centroid for a triangle is h by 3 from the base. For rectangle it's h by 2 from the origin, and for circle it's h by 2 from its center, and h here is the diameter. So these are the value for different shapes, and that can be used in the while converting the distribution force into a point load. So that's it for today. In the next class we will try to calculate the centroid for more complicated shape, and then we will move to the beam problems. So yeah, that's it for today.
Thank you, Mansoor.
Yeah.